G'day guys, and welcome back to Up to Speed with Elasticsearch. In this video we're going to be looking at chapter 4, which is search continued. So in chapter 3 in the last video we were looking at search, which includes full text analyzed searches and non-analyzed searches. In this video we're going to continue that, and I actually have potentially some good news for you guys, as you might be able to tell judging by the slides that I have on the left hand side. We don't actually have any more theory to cover in this video, or possibly in the next couple of videos as well. So the next few chapters, starting from this chapter, are going to be very hands-on, which hopefully is a good thing. So let's get right into it. We have a few tasks to complete, starting with the Shakespeare index. And the first task that we're going to be looking at is some interesting behavior that we noticed in the last video. So we tried to do a case-insensitive exact match search on the word enter pons. And we weren't getting any results. So let's try to remedy this first. So as always, I'm going to copy the instruction because it's handy to keep this in the Kibana console, just so that you don't forget what it is that you're trying to do. So let's jump into Kibana, check our indexes. We've got our Shakespeare v1 index available here, and I'm just going to drop the instruction here. And to just reproduce the problem for you guys, if we try to do something like we'll run a search on Shakespeare, and we run a query, and we want to do a term query on the text entry field, and the value is going to be enter pons, and we want this to be case insensitive, and set this to true. We get back no results, despite the fact that if we run another search, run a query, this time we'll use a match query, or maybe even a match phrase query, and the field is going to be text entry, and we want this to be, again, enter pons, and we'll try running this. Oh, we still get nothing. Have I points with an I? There we go. Okay, so we get back two entries here, but notice in the second entry, this contains this extra token re, and we want to avoid that. So even if I add the extra I in the second case, we get back no results. And the difference between the match phrase and the term is the match phrase is going to be looking for these tokens, enter and points, in this order. So it's not going to filter out additional tokens that are before or additional tokens that are after this particular phrase. Whereas if you want literally an exact match, a term is what you're after. A term query is what you would use for searching for some kind of an ID, for example. And it's curious that despite the fact that we're using the same value and telling it that it's case insensitive, we're getting back no results. And to understand why, we need to look at the index itself. So let's run a get on Shakespeare /mapping. And let's scroll down to our text entry field. Notice that this is actually a text field, and the term is a non-analyzed query, which is going to behave very strangely if we try to run it on a text field. So what we kind of need to do here is we want to index text entry in different ways. We want text entry to be both an analyzed field supporting full text search queries and a non-analyzed field supporting non-analyzed queries like this. So we're going to need to adjust the mapping. So I'm going to create a new version of the Shakespeare index with this change in place. So let's go ahead and do a put Shakespeare v2. We're going to have some settings, the settings that we need. You know what? Yeah, let's just go ahead and rewrite these. We want the number of shards set to 1, and the number of replicas set to 0, because remember we're on a single node cluster, and a replica can't live on the same node as its primary. Since we only have one node, it means we can't have replicas. And then we're going to have a mapping section. We want dynamic set to strict, so that you can't add documents with fields that don't already have an existing mapping. And we're going to have some properties. Those properties largely are going to be the same as what we have here. So I think I can just paste this in. And let's auto indent this. The difference is we want to give text entry a subfield. So we want to keep it largely supporting full text search. So if you just search on text entry, that's going to be full text search. But if we want to give people the option to search on this field in a non-analyzed way, we can add a subfield for it, a child field. So in the mapping, we can add a fields array or a fields object, and we want to add a subfield to text entry, and we're going to call this keyword. We don't have to call it keyword, we could call it anything, but we're going to call it keyword because that's going to be the type of the field. The type of the field is going to be a keyword field. Okay, so let's go ahead and run this. Sounds good. And let's reindex the data. So we'll run a post to reindex the source is going to come from Shakespeare v1. So we're copying the data from Shakespeare v1 to Shakespeare v2. And the destination is going to be Shakespeare v2. Go ahead and run this. Cool. 10,000 documents got created, so looking good. Let's try running this again, but on v2. So I'll run this again on v2 just to make sure that the data is there. So yes, we're getting the same data, enter pons and enter points and re-enter points. So we'll run a text entry based search, which is case insensitive on text entry. Now I suspect this itself won't work, but we can now access that child field that we created. So we can run text entry dot keyword, and notice how we're getting the auto completion now. So we've got this child field of text entry, which is a keyword based field. So let's run this, and what do you know? We get a match. So yeah, that addresses the problem or the peculiarity we ran into in the last chapter. And I'm kind of glad that it happened, because it gave us the opportunity to look at child fields, subfields, and look at indexing records as both full text and non-full text search. So this is how you would deal with a problem like that. Okay, so that's our first task done. Second task, on the Shakespeare index, we want to be able to scroll through 10 results at a time. So I'm going to, you know what I might actually do? I'm going to move the alias from Shakespeare v1 to Shakespeare v2. So I'm going to say remove. The index is going to be Shakespeare, and the alias, Shakespeare v1, and the alias is going to be Shakespeare, and I want to add, the index is going to be Shakespeare v2, and the alias is going to be Shakespeare. Cool. Let's move that alias over, and if we do a get on Shakespeare now, we should be pointing to the v2 index, which we are. Great. Okay. I'm not bothered to delete the v1 index, we can leave it around, but in practice, after you've performed this re-indexing of data and moved the alias over, you could consider getting rid of the old one once you're certain that you don't need it anymore. So with that out of the way, let's go ahead and address the task. Oh, sorry, that's the wrong text that I've copied. Here we go. Beautiful. Okay, so we want to scroll through 10 documents at a time. Well, let's just do a search on, and you know what? Let's maybe even modify this. I'm going to modify this to 5 results at a time. So let's just do a search on Shakespeare. Get Shakespeare _ search. And we're not specifying any criteria here, so we're getting back 10,000 hits, which makes sense because there's no search criteria, so all of the documents in the index are matching the search, which is empty. And we're getting back, by default, 10 documents. It'd be nice if there was a way to see this, but we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're getting back 10 hits by default. And we want to change this so that we can scroll through 5 results at a time. So what we can do is, firstly, we can specify the size parameter to 5, and this will limit the number of results that we get to 5. 1, 2, 3, 4, 5. And to add a scrolling sort of behavior, we can add a from parameter as well. So if we've already scanned through the first 5, we can then skip the first 5 to show the next 5. I don't really know the order of the documents in the index, and I'm not too familiar with the data that's in the index, so I can't say for certain that this is the next 5, but let's just try it again. We'll say from 10. So the first record here is enter King Henry. So we'll try running this again, and the first record here is now an interesting document that doesn't really seem to have too much. We can bump that to 15. And yeah, we seem to be looping through the documents, skipping 15 and then taking 5. I will mention that this approach isn't really suitable for deep scrolling, so scrolling through thousands and thousands of documents. There is another approach that's better suited to that, but if you're only paging through a small number of results, like what a human would probably page through, then this approach should be fine. Cool. Okay, so that's the second task. Third task, add highlights so that our search term gets highlighted in the results. So let me copy this and we'll get that implemented. So for starters, let's run a search on Shakespeare. And let's just use maybe one of the previous searches. So if we want to run, say, a match on text entry, and the match should be, let's say, Henry, or perhaps King Henry. There we go. So we've got a few results here. All of them mention King Henry, but whenever you are building a search application, sometimes you'd like to highlight where the matched content lives in the document. So the way that you can do this is, let me see if I remember where to put it. After the query, or before the query, basically outside of the query, there is a highlight option that you can use for this purpose. So we need to provide a few things to this, but the first one is going to be the fields that we're interested in highlighting. So I think this can be an array, and we're after text entry. Let me just make sure this works. No, it needs to be an object. Okay. Text entry. Let's try that again. Okay, seems nice. And we can see this is already actually working. So text entry is coming back in a highlight object, and it's wrapping both terms, King and Henry, in these EM tags. Now, if you were after King Henry as a phrase, we already know what to do here. Change match to match underscore phrase. Try that again, and now we're only getting King Henry as well. It's not going to be highlighting Prince Henry, for example. It's only going to be highlighting King Henry, which is the exact phrase that we provided. Now, you might not want EM to be the characters that are used to wrap the highlights, and you can configure that. So you can configure a where is it? Not on the field, sorry. You can configure a pre-tags. Again, I feel like this is an array. And let's say we want to use B tags. And you can configure post tags. And I'm going to try this as an array again, which is going to be /b. So instead of em/em, I want this to wrap in b/b. So let's try this. There we go. And we can see King and Henry wrapped in B and /B tags, so that if you were to render this on a web page, this would appear as bold. Awesome. So I think there are other configuration options that you can play with. For example, you can specify minimum and max limits to how much content gets rendered here, which you might want to do for performance reasons if you have really large documents. But just to get you started with highlights, I think that's a good starting point. So that's the highlight task done, and I think for now we're done with the Shakespeare index. Let's move over to Apache. With Apache, we only have one task, which is to perform an asynchronous search. This is something that I haven't introduced yet, so let me just copy this and we'll look at what this is. So I think I can get rid of this, and I'm going to jot down the instruction, asynchronous search. So to start off with, let's do a search on Apache logs. So we'll do a get Apache logs underscore search. And notice how we get results immediately. And that's because we haven't specified any query, and we're not asking for a huge amount of data. We're only asking for 10 records. But if you have a situation where you've got somewhat of a complex query, in your query, if you've got a lot of decision making happening and your documents are quite large, maybe you're dealing with book contents or maybe even web page contents, and the contents of each document is quite large, and you're asking for a large result set, it might take a few seconds, maybe even longer, to process all of that, depending, of course, on all of your circumstances. What query are you running? How many documents are you getting back? Are you doing deep paging? Are you skipping a bunch of documents and all of that stuff? The configuration of the node, all of that can determine how long the search actually takes. And if you are in a situation where you've got a long-running search, or you're expecting a search to be a long-running search, instead of keeping the request there, waiting for results to come back, which if this is a user-driven search is probably not going to be ideal, you can have ElasticSearch return control to you immediately and perform the search asynchronously in the background. And then later, you can retrieve the contents of the search to get results asynchronously. So even though we don't really have really any practical way of making this a long-running query, we're still going to demonstrate the asynchronous search so that if you are in that situation, you are familiar with how it works. So to start off with, instead of search, there is an async search method that you can call, but the HTTP verb needs to be a post. So let's try this again with Apache logs underscore async search. And I'm not going to specify any search criteria, but I am going to specify a query parameter to the request. To start off with, let's just go ahead and run it. And notice how we got results back immediately. And that's because it was a very quick search. So there was no reason for Elastic to make it asynchronous. But you can force it if we specify a query parameter called wait for completion and set this to 0. So we're giving Elasticsearch, I'm not sure if this is seconds or milliseconds, but we can check the documentation for that if we want. But I'm giving it 0 units of time, 0 seconds or 0 milliseconds. I can't quite recall which it is. We're giving Elastic 0 seconds or milliseconds to perform the search. And because the search, of course, can't complete instantly, it is going to run asynchronously if we add this. So let's go ahead and run it. Wait for completion. Why not? Let me check the documentation, actually. Yeah, okay, let's check the documentation for async search. I will mention one little trick that I've noticed. Whenever you're looking at Elastic documentation and you want to look at a different piece of documentation, unfortunately there isn't a way to open search results in a new tab. So I find myself copying the URL, opening a new tab, and then pasting it in so that I don't lose what I was looking at earlier. So we want to look at async search. Async search, here we go. And the field that we're after is that wait for completion field. Wait for completion timeout, that's it, okay. There it is. Try that again. Okay, so now we get back no results, and we get back this ID, and you can see has the query retrieved any results? Yes, it has. Is the query still running at this point in time? Yes, it is. And here's our ID that we can use to refer to that query later. So if we want to get results from that query now, we can say get Apache logs async search. Oh, sorry, needs to be a post Apache logs async search, and paste in the ID and run it. Oops. Maybe it can be a get. Sorry. We'll do a get async search. There it is. Paste in the ID. And we get back some information about the asynchronous request, and we get back all of these results. And you can see is running is now false, which means that the asynchronous search query has completed. And yeah, we're able to return all of this information to the consumer or wherever it needs to go. But one other thing that we should keep in mind is this asynchronous search ID is still alive and living in Elasticsearch. I think that it will get cleaned up eventually, but if we're done with it and we know that we're not going to need this anymore, we can actually save Elasticsearch from having to clean this up later by deleting the asynchronous search results. So we can delete this and run this. Okay, cool. Let's try to retrieve it, and as expected, we're getting back a resource not found because we cleaned it up. So that's a nice little feature to be aware of. And I think we're done with, you could say, sort of basic searching. The next thing for us to go through is custom analyzers. So we're back on the Shakespeare index. Sorry guys if you don't like Shakespeare. Which probably includes myself. What we want to do here is we want to use one of the more advanced features of Elasticsearch, which is custom analyzers. As we've seen in the last chapter and in this chapter, we can use match and match phrase, and there are other full text search queries that we can use as well, which operate in a full text search sort of way. But sometimes we want more control over that. So a scenario that we have is we want to support searching using Arabic numerals instead of Roman numerals. So for example, Act 2 instead of Act 2. Let me copy this and I'll show you what I mean by that. Let's just paste this in here. And sorry, I did a compulsive Command S. Let's just have a look at the Shakespeare index. So we'll run a search on Shakespeare, and we'll run a query, and we want to perform a match on the text entry field on, say, Act 2. And we're getting back results, but if I change Act 2 to Act 2, we will still get results because there will be matches on Act, but nothing will match on 2. So if I run this, we get back things like Act 1. We do get Act 2, but we also get Act 3. So it's really just results that are matching on the Act, and this 2 isn't really being used at all. And we would like to customize the behavior of the index so that this does actually work. So as the instruction says, we're going to need to use a custom analyzer to achieve this. And I've specified there is a particular feature that we're going to need to add to the custom analyzer, which is a synonyms token filter. What that's going to do is it's going to basically say that the Arabic numeral 2 is going to be synonymous with the Roman numeral 2. And we'll do this for 1, 2, 3, 4, 5. Since I think there are only 5, maybe even only 4, but I'll do it up to 5. Yeah, it's going to treat Arabic numeral 2 and Roman numeral 2 as synonymous. And as the instruction says, we are going to need to create a new version of the index with the new analyzer. So custom analyzers are great, but they live on the index. So if you ever need to add a custom analyzer or modify one, that is going to mean changing the index, which probably means new version. Okay, so we've already done this once in the video. We're going to create a version 3 of the Shakespeare index. So we'll do a put Shakespeare v3. Settings are going to be number of shards set to 1, number of replicas, number of replicas set to 0, and the mappings is not going to change. So I'm just going to grab Shakespeare v2 mapping, and we're going to copy all of this, in fact, maybe even from here. So everything within the top 2 curly brackets. Paste this in, and I'm just going to format this just to see if there's any dramas with it. I think it's okay. Yeah, that looks good. Yeah, that looks good. Okay. Now, as for the custom analyzer, the analyzer lives under the settings. There's an option here called analysis. And the syntax is a little funky, so I'm actually going to refer to the documentation. So here is the documentation for a synonym token filter. This is what we want to use. So I'm just going to scroll down, and this is, so you can use the synonym token filter in a couple ways. One way is with a file that lives on the node. We don't want to use this method. We want to provide the synonyms in the request. So this is what we want. So I'm going to copy this content here. I think that looks about right, and paste this in, auto indent, and that looks good. So the we are not using any character filters. Remember, there are 3 parts to an analyzer. There's a character filter, which filters the stream of characters, a tokenizer, which breaks up the characters into tokens, and then token filters, which then filters or modifies those tokens. So we're not using any character filter here, and I think that's fine. We don't want to modify the stream of characters. We're using a standard tokenizer. I think for now that makes sense. And then we have, copied from the example, we have two token filters. One of them is a stop filter, which adds stop words, words that are not analyzed. This is not too relevant for us, so I'm going to get rid of it. And I'm going to get rid of it from this filter object as well. And now we only have one token filter, which is a synonym token filter. Synonym is also the name of our custom analyzer here. And I'm going to leave that as it is. The type of the analyzer is a synonym analyzer. It's set to lenient, which means that if there are any, I believe, syntactical problems with our list, it will basically make a best effort in terms of mapping these. And now for the actual synonyms. So we want a synonym of I. We want I to be synonymous with 1. We want double I to be synonymous with 2. Triple I to be synonymous with 3. Roman numeral 4 to be synonymous with 4. And Roman numeral 5 to be synonymous with 5. Okay, so this is going to add the analyzer to the index, and that is fine. I think well, I'm kind of debating as to how many different variations we want to demonstrate, but in the interest of time, maybe we'll set things up properly the first time. So we've got our custom analyzer on the index, but if we don't specify that our text entry field is going to use this custom analyzer, then we need to be specific in the search request every time that this field needs to be searched using this analyzer. Like, we need to include that analyzer in the search every time, unless we also specify that this field uses that particular analyzer. So let's go ahead and do that. Let's say, where are we? Analyzer. And we want to set this to the synonym custom analyzer that we created. So I think that's looking good. Let's go ahead and save the index. Cool. And before we re-index the data, let's try it out. Let's just do a get on Shakespeare v3, and we want to use the analyze endpoint. So let's specify the field. So the field here is going to be text entry, and the value or the text that we want to analyze is going to be act. Let's say act 2. Cool. Okay, so we've got act and we've got 2. Notice how the double I got converted into the decimal. And same thing if I use decimal here. It's of course remaining as the decimal, but the point here is that the Roman numeral variation and the decimal variation are producing the same token because they're synonymous, and you can kind of see based off of the type of the token how that's working. There is one problem that I've noticed though, which is that act has a capital A, and just to prove this is true, if I replace all of these with uppercase variations, they're all remaining in uppercase, and that tells me that we need to make one more change to our to our custom analyzer. So we've got the synonym token filter working, but there is one other token filter which I'd like to add, which is a lowercase token filter. After processing the synonyms, we want to lowercase all of the tokens so that we're able to search in uppercase, lowercase, or something in between, and it won't matter. So we'll just add a lowercase token filter to the filters array. I am going to need to delete the index and recreate it because I'm modifying it. So that's why I didn't perform a reindex. I didn't add any data to it, which is probably a good practice. If you're adding custom analyzers or you're changing the mapping of your fields, it might be worthwhile to just run a quick analyze and make sure that everything is working as expected before you actually load up any data. So let's go ahead and delete it and we'll recreate it. Okay, now let's try this again. Beautiful, and you can see that act is now lowercase, which means that when we're searching, we can search using act in lowercase, uppercase, or some crazy middle ground. Now we can reindex, so we'll run a post reindex, and we're going to specify the source index is going to be Shakespeare v2. Yep, and the destination index is going to be Shakespeare v3. Let's run this. 10,000 documents created. Let's run a search. So get Shakespeare v3 search query. We'll do a match phrase where the text entry is Act 2. Boom, and we get back Act 2 and Act 2, even though these are in uppercase and with Roman numerals. Thanks to our custom analyzer, we now have a lot of flexibility in how this works. If we wanted to, we could still use Act 2 and get results, but we've got more flexibility now in terms of how we can query. Cool, all right, so before I forget, I'm gonna move the alias over to Shakespeare v3. So let's just run a post to aliases. We want to specify some actions. The first action is going to be a remove. The index is going to be Shakespeare v2. The alias is going to be Shakespeare. And we want to add to Shakespeare v3, and the alias is going to be Shakespeare. Let's run that. Awesome. Okay, and if I do a get of Shakespeare, it's pointing to Shakespeare v3. Now, before we wrap up, there is one other topic that I wanted to cover in the video, which is aggregations. So we're not going to do too many of these, but there are a couple just to introduce you to what they are and how they look. So sometimes when you run a query, you're not really interested in the data itself, but you're interested in an aggregation of the data. So kind of like getting statistical information, min, max, average, or answering questions like how many GET requests were made in each day, or how many lines does each speaker have. We kind of want to take the data set and aggregate it, group it, and do all of that sort of stuff, and answer some questions about the data set as a whole. So let's start with the Apache index. I'm going to actually copy all of this content so I don't have to keep coming back. And I'm just going to comment these up. And we'll start with the Apache index. What's the min, max, and average number of bytes for each document? So let's run a search on Apache logs. And our query isn't actually going to be present. We're not interested in searching, we're interested in aggregating. So because we're interested in aggregating, we don't actually want any hits. If I just run this, we're getting back documents from the Apache index. We don't want documents. We want answers to these questions. So we're going to specify the size to be 0. And if I run this, we get back no hits. which is kind of good, but we want those answers, min, max, average, for the number of bytes. So to perform aggregations, instead of query, you can use aggs. And as you might imagine, there are different types of aggregations. And firstly, our aggregations need to be named. So we want the max number of bytes. So I'm going to call my aggregation here max bytes. The aggregation type is going to be a max, and the field is going to be bytes. So let's run this. And I can see, wow, that is a pretty massive document. It's an exponent. I'm a little curious to know what that document was, but maybe we'll come back to that. Let's perform the other aggregations that we're after. We're also after min bytes, which is going to be a min aggregation, and the field is going to be bytes. So the lowest or the smallest number of bytes for a document was 35. And then we want the average. So let's just say avg underscore bytes. This is the name of my aggregation. And this is going to be an average aggregation. The field, again, is going to be bytes. So the average looks like it's, what is that? About 300 KB? 300 KB. Awesome. So as you can see, yeah, aggregations are useful for answering these sorts of questions. We do have different types of aggregations though. Some aggregations, which we call metric aggregations, produce you a metric, produce you a single number like this. But sometimes you don't want a single number, you want to create groups out of things. And if I just check the documentation for aggregations, and it's a good idea to become familiar with the Elasticsearch documentation and get used to searching it. We've got three types of aggregations. We've got bucket, metric, and pipeline. Pipeline are where you combine multiple aggregations together. We're not going to look at pipeline aggregations in this course, but they function very similarly to the other two. We've already seen metric aggregations where we're producing a metric, producing something like an average or a max or a min. The other type of aggregation is a bucket aggregation, which is more like a group by. So that's kind of like what we're dealing with here. How many GET requests were made in each day? So we want to create groups for each day and then get the number in each group. So we'll do something similar. We'll do a get Apache logs search. We're going to set the size to 0. Because if we don't, look at what will happen. I mean, it's still fine, but you get back all of this extra noise. You don't actually care about this stuff. You just care about the aggregations at the end. So to save Elasticsearch the performance penalty of retrieving the hits, and also to make the response more readable for you, it's advisable just to set the size to 0 when you're only interested in aggregations. I will mention that sometimes you do want to run a query. So if you only want your aggregations to aggregate data based off of a query, you can include the query in the request. And these aggregations will only be run on the query. But otherwise, if you want aggregations to run on the whole dataset, just don't include a query and it will run on the whole dataset. Okay, so on to our next aggregation, which is how many GET requests were made in each day in the dataset. So we want to use aggs again. Aggs is short for aggregations. The name of this is going to be something like GET requests per day. And the type of aggregation is we want to run a date histogram. So the field is going to be, I think there is a timestamp field that we can use. If you're ever not sure, you can always run a get Apache logs mappings and check out what fields you have available. Maybe even also you could just run a search and get an idea of what data is inside each field. But timestamp looks like the one that we're after here. and the interval is going to be a day. Now, Elastic is going to complain because interval is a deprecated field, but let's just run it. And it's telling us to use either fixed interval or calendar interval. So we're going to use calendar interval here, calendar interval, just to make Elastic happy. Cool. And we're getting back this buckets array. Buckets are like groups. So you can see here key as string is the 17th of the 5th, 2015, and there were 1,632 requests in that bucket. Actually, I've just realized this isn't giving us exactly what we're after. We're after get requests only. So as I mentioned before, you can include a query in this, and the query that we're after is going to be a term query where the verb is get. So we should see these numbers drop. 1632, 2893, 2896. So these drop slightly, 1626, 2881. So most of the requests do appear to be get requests, but now, as you can see, those numbers dropped. So the aggregation is only running on results of this query. Yeah, so each bucket is its own group. Each group will have a key, which is going to be, the key of the group or the ID of the group. And that's the answer. That's the answer to that question. We do have one more aggregation to run, which is on the Shakespeare index. How many lines does each speaker have? So I'm just going to run a get on Shakespeare search, and we're looking at the v3 index. Each document has a speaker. So whenever somebody says something like King Henry, the speaker is present in the speaker field. So I'd like to know how many lines does each speaker have? How many lines does King Henry IV have, for example? And let's go ahead and do that. We're going to use another aggregation. We'll set the size to 0, and we'll run aggs. The name of the aggregation is going to be lines per speaker, and the aggregation type is going to be a terms aggregation. The field is going to be speaker, and we can limit the number of buckets or the number of groups that we get back. I think I'm happy with the top 10. So when you ask for buckets, Elastic will sort these from largest to smallest. Let's go ahead and run this, and we get back a character named Falstaff. Don't really know who this guy is, but he seems pretty popular. 654 lines. Hotspur 853. Prince Henry and King Henry, and so on. Cool. So I think that's really all I wanted to cover around aggregations. They do get more complicated, just like if you can imagine grouping in relational database and SQL. They start nice and simple, but they can get quite complex, and the same is true for aggregations in Elastic. I don't want to go through all of the different variations that you can run, but I just wanted to introduce you to the concept. And for answering simple questions like this, the aggregations are nice and simple. So I think that's all of the content that I wanted to cover in this chapter. I did have some homework for you if you wanted to try performing a task on your own that we haven't solved before. So if we order results in the Shakespeare index by speech number, let's just do a get on Shakespeare, Shakespeare / search, and we sort by speech number in ascending order. Where are we? So we start with 1. Is that right? Yes. Oh, that wasn't. too useful. Let me set the size to 100. Was it speech number? What about in descending order? Let me add a query to this. Let's say we want to do a match on text entry king. Okay, here we go. So we can see an entry with speech number 7 appears before an entry with speech number 66, even though we're sorting in descending order. So 66 should appear before 7 if we're sorting in descending order. That's your challenge. If you would like a challenge, you're going to need to look at why that's happening and then correct the index so that this works. I might start the next chapter with a solution to this problem, but if you'd like to try to solve this on your own, here's a good one for you to have a go at. So thanks very much for watching, and I'll see you in the next chapter. Bye.